Okay, so in the previous slide, we talked about the line search method. So line search method will find the best epsilon, best learn rate. It is not finding the best direction. Okay, so it assumes that we have direction based on the gradient. Okay, given this direction, then what is the best step size? What is the best learning rate? So assume a quadratic function like this, and then this is a gradient. And then let gt be the gradient. Then in the exact line search, epsilon t will minimize this function. Okay, so from wt we calculate the derivative of this function, and with this gradient, so now gradient is fixed. Okay, gradient is given, and then with a different learning rate, we are going to minimize this function. So don't get confused. We are interested in minimize this function with w. Okay, and with w we actually took derivative, and then we found the direction of the learning. So we have the direction. Then now this is another problem. So we fix the direction, then how much we have to take the step? That's the question. And then we can minimize this function with this learning rate. Then the next step, wt plus 1, the function of this one is actually a function of wt minus epsilon gt. Okay. Then we can actually replace this w with wt minus epsilon gt. So now we have this one. And this one is a minimization problem too, right? Then we can take a derivative of this function with respect to epsilon. Okay, again, this one is different from this one. So we are talking about another problem. And when we take a derivative of this function with respect to epsilon and set it to 0, okay, and then replace b plus h times wt with gt. Okay, you can do it by yourself. It's not that complicated. Take a derivative of this function with respect to epsilon, and then you will have some equation and set it to 0. Then move some term to the right side, and then replace this term with this one. Then you will get this. So it means epsilon t is the step size of this. Okay, so again, we found this gradient based on this one. Okay, so now we know where to go, and then the question is how much to go. Okay, so epsilon defines the best length. We are not talking about the direction here anymore. Okay, but the line search method is not used most of the time because it involves this Hessian, and we don't like Hessian that much when the parameter is in a high dimensional space. So instead of using this exact line search, then we come up with some simple idea. Okay, now in this slide, we are going to talk about the direction of the learning. Okay, so in the previous slide, we talked about the step size. And from now on, we're going to talk about direction, or sometimes we'll talk about the learn rate too. So the first one is momentum. So momentum is about the moving average of the gradient, and it will accelerate learning, and especially for small or and noise gradients. So in SGD, with the large epsilon, it could follow this trajectory. Okay, so this is not that beautiful. It looks ugly, but it converges. Okay, good. But with a small epsilon, it goes smoothly. Then we need a lot of steps. Okay, but eventually it can go. But the problem is plateau. Okay, so when the gradient, the step size is small, then it will stop around here because gradient is 0. Then we cannot move, we cannot escape. We cannot move around here. But if we have a momentum, then we can get out of this plateau. So think about uh, think about some play. Okay, so we are running a ball from this hill. Then when we have a plateau around here, then ball can actually run and run because there is a momentum. So ball was running from this hill, then we have actually there is a velocity there, and we have energy, right? And based on that energy and with the velocity, then we can go through this plateau. The ball can go through this plateau. So likewise, we can actually use that momentum in the learning process. So, and this momentum is actually accumulated gradient. So let's take a look at this algorithm, SGD with momentum. So we have learning rate and the momentum factor alpha, which is usually 0.99 or 0.95 or so. And we start from random parameter, and the initial velocity is 0. So at the beginning of this learning process, then the velocity should be 0. Okay, then we have a stopping criteria, and we take a sample as in the SGD, and we calculate the gradient. Okay, so far it's the same as before, and then instead of update the parameter directly, then we update the velocity first, like this. So at the beginning of this training, the v was 0, but as training process goes on, then we can accumulate this velocity. So eventually, at these situations, when we are here, then the velocity from the first step is accumulated. Then now, when we are here, then still we have some velocity. Okay. Then with that velocity, we will update this one. So in this algorithm, when the alpha is 0, if the alpha is 0, then the v is actually minus epsilon gradient. Then that is exactly the same as this algorithm. W is W minus epsilon 0. That is a simple SGD algorithm. And when the alpha is 0, then it's exactly the same as simple SGD. So alpha defines the momentum. Okay. And there is another popular momentum, which is Nesterov accelerated gradient, which is, in theory, which is more attractive than the simple momentum. But when we apply, then it's almost the same as, in my experience, it's almost same as a simple momentum. But in theory, it's more attractive. Okay, let's talk about the regular momentum first. Okay, so gradient is average of the gradient of the mini batch, and the velocity is defined by this. Okay, and this one is parameter update. Okay, but in this specific extreme example, okay, W is here, and this one is gradient direction, but there is a momentum here. Okay, then W will go to this place because we are using this to update, right? So we know this one is the best place, but the gradient knows where it is, but this momentum ruins that direction. So sometimes this could happen, but again, based on my experience, this kind of case was not that popular, not that often, maybe, but my experience is quite limited, so you can try this NAG. Okay, NAG would be much better than regular momentum. But NAG, let me explain what NAG does. The idea is simple. So when W is here, then we know the momentums. Okay, so we know the velocity. So which means no matter what kind of gradient we have, then we know we will move this much. So look at this one. We have a momentum and we have a gradient at this point, then we will move this direction. So we take this direction anyway. No matter what kind of gradient we have, this is fixed already before calculating the gradient. So this gradient direction is not that informative in this case. So this one is not considering this momentum. But in NAG, no matter what kind of gradient we have, we will move this direction anyway. So if we move this direction, then when we calculate the gradient, let's consider this movement. So when we take a derivative, we actually move this one to this direction first, and then calculate the gradient at that point, which means we take a derivative at this point, and the gradient will give us this direction. So compared to this momentum, this one is better. Okay, so in theory, it looks better than this, and the computational cost is not, that is not more expensive than this one. So NAG looks better. Okay. Okay, then the next one is ADA-GRAD, adaptive learning rate for primaries. So as I said, the learning rate is one factor to determine the effectiveness of the learning process. So in the ADA-GRAD, we will change the learning rate adaptively. Okay. So initialize the cumulative variable r with a zero vector. Okay. And the other parameters are the same as before. So learning rate and initial parameters, they are initialized in the same way, and we use the same stopping criterion, and then take the mini batch. So far so good, and compute the gradient for the mini batch. So far so good. And this is the difference between the previous one and the other grad. So accumulate the squared gradient r. So this one is actually the element-wise multiplication. Okay, so the r is the amount of gradient. Okay, so accumulated amount of gradient, which means, at the current point, r says, oh, we took this many steps. This we have been updating this much. Okay, so r defines that, and then when we update the parameter, then this is kind of the learning rate. Okay, and learning rate gets slower. This is the beauty of this ADA-GRAD. So when we talk about the learning rate, the large learning rate and small learning rate, I said in the beginning of the training process, we prefer the large learning rate, and when it converges, then we prefer small learning rate. But we don't know when it is converging. But still, so as the training process goes on, then we prefer the smaller learning rate. Okay, so every time we increase r, okay, then when r is large, it means we have been updating a lot. Okay, then When R is large, then the learning rate gets smaller. Okay, so gradually it gets smaller and the learning gets slower. Okay, so that's what we want. Decreasing the learning rate is good strategy, but the problem is we don't know when to converge. So if the learning rate gets lower too fast, then we'll lose some chance to update our primers. So that is actually advantage, and at the same time that is disadvantage depending on the situation. An RMS prop was proposed to resolve undergrads radically diminishing learning rates, as I said. Let's take a look at this algorithm first. And we have the same kind of criteria and sample mini batch and compute the gradient. So far, so good. But when we calculate this R, in the other grade, the R was just accumulated, but in the RMS prop, instead of accumulating, we actually get the moving average of the squared gradient. So this row is somewhere between the 0 and 1, so it is actually the average of R and the squared gradient. So it cannot go too fast. I mean, it is not accumulating. Okay, and the updating rule is the same as other grade. So only this R is slightly different. So only this difference is making different algorithm. And I think RMS prop is more popular than other grade. And we can add a momentum to RMS prop. So in this case, we have NAG, Nesterov accelerated gradient. Okay, so the steps are the same, but instead of calculating the gradient, we calculate NAG. Okay, and then R is the same as before, and we have a velocity, and we update. So the optimized algorithms are slightly different from others. Just one step is different, and that makes difference in the training process. And next one is Adam. So Adam is another really popular learning algorithms. Okay, so Adam is a variant on the combination of RMS prop and momentum. So we have another parameter, row 1 and row 2. Okay, and we have first momentum and second momentum, S and R. And take a mini batch and calculate the gradient. In this case, it's not the Nesterov accelerated gradient, it's a simple gradient. And then we calculate the accumulated gradient and accumulate the squared gradient. So this one is the same as RMS prop, but this one is slightly different. And the correct bias in the moment. Mainly there are two differences between Adam and RMS prop. First one is first moment. In RMS prop, they use Nesterov accelerated gradient, and the second moment is exactly the same as RMS prop's equation. Okay, that is the first difference, and second difference is this correct bias equation. In early training process, S could be biased. So bias means expectation of S is different from expectation of G because S is moving average of G. So if the G is stationary, then they should be the same, but that's not the case. And the expectation of R is not the same as G square. Okay, because R is moving average of G square. Let's say this one is a G square here, and then the expectation should be the same, but that's not the case because in the beginning of this training process, S and R were initialized as zeros. So in the beginning, S is quite small. S is 0.1 g, and let's say the first gradient, and r is 0.001 g1 square. So this is quite a small number, and since we have this, it is changing a lot. Okay, so instead of using these two numbers, we can actually correct the bias. So by this one, in the first iteration, S hat will be G1 again, and R hat will be G1 square, this one. Okay. So gradually, when we repeat again and again, then this effect will fade away. But in the beginning, this is really unstable, and it makes some bias. So Adam algorithm actually corrected this bias. That's what this line says. We have been talking about a couple of different optimizers. So in deep learning or in neural network, we cannot try all different kind of combination here. So first, we can try SGD, SGD with momentum, and RMS prop, and Atom. Okay, so at least you have to try these optimizers because we don't know which one is the best for your application. Whatever is the best for your application, that's the best algorithm for your application.